Okay, so today we're going to kind of switch gears here. The first 4 sections of calculus is all on this idea of the tangent line problem, and this is called differential calculus. We've been dealing with this type of problem for, 12 weeks, 13 weeks now, on how to find the rate of change at an instant. So the slope of this tangent line, and then we did applied problems. So we talked about, when is it 0? What's the critical point? We looked at being able to graph the functions based on these slopes at any given point to know when a function's increasing is when I have a positive slope, decreasing when I have a negative slope. So being able to find the equation of this line, we spent 4 chapters on that. Chapter 5 is all about this new idea, and this new idea is called integral calculus. So we have a function, and the application of this integral calculus is to be able to find the area underneath the curve, which would talk about if this, eventually we're going to apply it to maybe this is a velocity function, we can integrate the area underneath the curve and find displacement. And there's a few different other applications to it. But before we can get to this, we really need to be able to define what an antiderivative is. So today we're going to move to 5.2, and we skip 5.1. 5.1 is just kind of the overview of the area problem, this story. And you can look at that in your book, and it talks about being able to calculate this area. And some of the techniques we're going to go about, if we have time, is the algebra technique of looking at rectangulars and then eventually taking the limit as all these rectangles go to infinity, the number of rectangles we have going to infinity, or we can think about as the width going to 0. So we'll apply some limit techniques to be able to talk about the area underneath this curve, and then being able to apply the fundamental theorem of calculus, which is going to make this take about 2 lines versus 2 pages. So we'll do one example where we use this algebra technique of adding up the area of each rectangle, taking the limit as the width of the rectangles go to 0, and coming up with the number, and then we'll learn fundamental theorem of calculus and apply that. So it starts off with saying, okay, what if you want to find the area underneath this curve using geometry? Well, this is a rectangle. I can find the area of a rectangle, therefore I found the area underneath the curve. You can only do that on shapes that have straight lines, right? So you can decompose it into rectangles and triangles or various things. Or you can do it with shapes that are circular or semicircular. But you're really limited in this technique of doing that. So that's why you learn calculus. And we'll come back to some of the tables in this section. So 5.2 is the indefinite integral section. Today is the 15th. 5.2, the indefinite integral. This is going to be useful when we go to solve the area problem in calculus versus the derivative problem. So if I have a function and I want to find the area underneath the curve between 2 points, I'm going to have use this idea of anti-differentiation. This is the fundamental result about so it turns out these two differentiation and integrations are inverses of each other. So in algebra, you might have learned like addition and subtraction. They're inverses of each other. If I take a number and I add 2, and then I have the sum of those 2, and I subtract 2, I get my original number. Differentiation and integration are related like that. So let's take a function, the derivative of a function, Your book calls this capital F of x. So this is the antiderivative of smaller f of x. So it turns out this is saying the same thing, that if I integrate, and really there's a plus c here. We'll talk about that in a minute. If I integrate, we're not going to talk about the plus c at this point. So if I integrate this antiderivative with respect to x, I get out my original function. The plus c is here. And we'll talk about why that is. So really what I want to say here, that the derivative with respect to x of my function, f of x, is going to equal this capital F of x. So this is a true statement. If I take a function, I differentiate it, I call that capital F of x. So if I come in here and I integrate this on the left-hand side, I have to integrate it on the right-hand side. The integral cancels the derivative, and I'm left with lowercase f of x. So if I integrate the antiderivative, I get out the original function. So let's look at it. So let's call this f of x. This is an antiderivative. Meaning, if I find a function, this is an antiderivative of a function of f of x. So let's look at an example. Let capital F of x be 1/3 x cubed. So if I differentiate this function, what do I get? X squared. Which was one of the terms on one of the problems on your exam that a lot of you struggled with being able to do. You try to use the product rule or the quotient rule and then not differentiating 3. It got a little ugly. But here, what this is saying, now if I integrate x squared, I get 1/3 x cubed. Right? So let's just go. So what this would be saying, is there any other functions that I can differentiate and get here? If I differentiate this, I get x squared? There is. There's infinitely many, and that's called a family of solutions. So it turns out I can have 1/3 x cubed plus a constant, a c. If I differentiate this, I still get x squared. It doesn't matter what the c is as long as it's a constant, because the derivative of a constant is 0. So this plus c comes in handy and will be a very important concept later on when we talk about initial value problems. We know the derivative of position is velocity. We're going to learn that the integral of velocity is position. So if I give you a velocity function and ask you for a position function, you integrate it. So then you have a position function. The position of your particle depends on some initial position. So there's something initial value problems. So initial value problems, which come up all the time in differential equations.
Submit the page down a little bit. On the very top there, you have
Yes.
derivative of small f.
Yeah, I should have this would let's leave this to be small f and this big F. Sorry. I'm trying to use the book notation and then I switch them.
I think the book actually uses the derivative.
So maybe I just switched in the beginning. So let's go look exactly what the book uses so I'm consistent. But thank you. Okay, they say f prime of x. So equals f of x. So they're differentiating f prime of x. So let me just make a note. Your book says that the derivative with respect to x of capital F prime of x. No, they say f prime of x equals f of x, sorry. F prime of x equals smaller k. So if I integrate f of x, and I integrate the derivative, I get the original function. So this is what I'm using for here. And just, if you follow this, if I differentiate a function, I get that big f of x. If I integrate big f of x, I get little f of x. So here they're saying the derivative of big F, if I take a function differentiated, I get the original, I get f of x. So if I integrate f of x, I get the derivative of the original function. It's a little bit confusing to think of it in this case. If I integrate this function, if I integrate this function, I get this function. So if I integrate f of x, I get smaller f of x.
Well, you have to have a derivative in order to integrate, right?
At this point, that's what we're looking at, right? So if I integrate this derivative, if I integrate this function, if I integrate this function, I get its antiderivative. Its antiderivative is a function that I differentiate, I get this function. So getting too caught up on this notation, which I think, let's look at some examples of where this comes in. So I'm going to write these in two ways. So let's look at the derivative formula, which is something that we're used to. And then let's look at the integral formula. So let's start off with just the derivative with respect to x of x cubed. What is the derivative of x cubed? 3x squared. So that would say if I integrate 3x squared with respect to x, I get x cubed plus c. The plus c comes with the integration formula. Because if I differentiate this, I get this. Right? And it's called the antiderivative.
It's essentially reversing.
It's the inverse properties of
Yeah.
each other. So it's an operation I do on a function, I get a derivative. If I do the inverse operation, I get the original function. So we can do a couple more. Let's say the derivative with respect to x of square root of x. Well, we know that's 1/2 x to the minus 1/2, which I can write as 1 over 2 square root of x. So this is saying if I integrate 1 over 2 square root of x with respect to x, I get the square root of x plus c. It's easy to see when we go through these examples. What if I differentiate x to the n? What is the derivative of x to the n? Nx to the n minus 1. So that's saying if I integrate nx to the n minus 1 with respect to x, I get x to the n plus c. Now this is not ideal to have this here. I would want to really integrate. So what would be the integral of, let's say, x to the r with respect to x? This would be the preferred form, right? X to a power. The integral of x to the power, well, if I let's let r be n minus 1. So n is r plus 1. So from here, if I let this substitution, I have the integral of r plus 1 over x to the r dx equals x to the r plus 1 plus c, right? R plus 1 is a constant. So I can divide this side by r plus 1. I divide this by r plus 1. That gives me that the integral of x to the r is x to the r plus 1 over r plus 1 plus c. And then keep in mind that r cannot equal minus 1. So really, this is the preferred way to view the integral of x to a power. Because we don't always have to have it in the form of a derivative of a function. It's nice when we have that, but sometimes that constant might not be there. So before I go further in here, I just want to make a comment on Theorem 5.2.2. So let's note the Theorem 5.2.2. And 5.2 forgot what theorem that one was. 5.2.3 and 5.2.3. These are properties of integrals. So we've already kind of talked about this plus c. This theorem, 5.2.3, is going to be really useful when we integrate more complicated functions. So it turns out a constant times a function. If I know the integral of the function, then I know the integral of a constant times a function. It would just be the integral of a function is an antiderivative, so the integral of a constant times a function is a constant times the antiderivative. So I can pull that constant out front and deal with it. B is what you should expect because we know differentiation and integrations are inverses of each other, and I can I can differentiate a function term by term, so that tells me I can integrate a function term by term, right? And then I can also subtract. The integral of the sum of two functions is the sum of their antiderivatives. Same thing with the difference of the integral. The integration of a difference of function is the difference of their antiderivative. So this theorem allows me to do term by term.
Does it matter the sign of in front of the constant?
No. So let's look at some examples. Let's say I want to integrate 6x cubed plus 14x squared plus 32x plus 5 with respect to x. Well, I can do this term by term. So what's the integral of 6x cubed? X to the fourth would be in there, but I also have that 6 to carry through. And then what am I missing? So I have 6 because a constant, the integral of a constant times a function is that constant times the integral of the function. X to the fourth divided by 4, right? This is the form. So if I'm integrating x to the third, the integral of that is x to the fourth over 4. Plus, what's the integral of 14x squared? Here? How am I getting the... So from this, if I integrate x to the r, you know differentiating x to the n would be n x to the n minus 1. Well, integration is the opposite, or the inverse of that. So if I'm integrating something of x to the r, then the integral of that would be x to the r plus 1 divided by r plus 1. So if I integrate, so let me just write this out. If I integrate x cubed with respect to x, that's x to the 4 over 4.
So you just add 1 to the power on the top and divide by the new.
Yes.
Instead of subtracting one from the power
Correct.
on the top and multiplying.
Exactly, right? If I add something, it's the inverse of
Right,
it.
the inverse of it.
Yeah, right? Because in differentiation, I multiply by the power and subtract 1. In integration, I divide by the new power, but then I add 1 to the new power. So then looking at those theorems, I can do more complicated ones with that constant. I just leave that constant alone, deal with it later. And I only have to look at the power of x. As long as the power of x is not minus 1, right? Because if the power of x is minus 1, I would have an issue. And we'll talk about that specific case after we do some polynomial examples. So The integral of x cubed would be x to the 4th over 4. What would be the integral of 1/2 x to the 1/2?
1/2.
1/2
Divided by 2.
x to the
1. Just an x.
3, yeah, it's a bit-
1.5, right?
Oh, because you're adding whole.
Because you add 1, and I could write that as 3 over 2. Divided by 3 over 2. So this might look pretty ugly, but I can simplify it because I can deal with fractions. So I would have really,
2x over 4.
they're going to cancel. But I'm going to just write this out a little bit nicer. So the 2 here, x to the 3 over 2, 2 times 3. So the 2's are going to cancel. I get x to the 3 over 2 over 3. So the integral of 1/2 x to the 1/2 would be 1/2 x to the 3 over 2 divided by 3 over 2. But then I flip and multiply, so I get 2x to the 3 over 2 divided by 2 times 3. So that simplifies to this.
I don't see how'd you get the 1/2 x to the 3 over 2?
Well, the 1/2 stayed there, right? Because the 1/2 is a constant. And we looked at that theorem, and the theorem said a constant times a function. The integral of a constant times a function is that constant times the antiderivative of the function. And then, so the 1/2 stays there. The x to the 1/2, if I integrate that, this is not minus 1, so I add 1 to it and divide by the new power. So 1/2 plus 1 would be 1/2 plus 2 over 2, which would be 3 over 2. So 3 over 2 divided by 3 over 2. Right? So let's just look at,
Can I finish the top one?
yeah, we'll go back to it. The integral of x to the 5/2 dx. What's the integral of x to the 5/2?
So it would be 7 halves, yeah, x to the 7 halves divided by 7.
Which then I would write 2x to the 7/2 over 7. Of course, there's plus c on all of these. Because if I differentiate this, I get x cubed. If I differentiate this, I get 1/2 x squared. If I differentiate this, I get x to the 5 over 2.
So for the top one, would we have to do like plus 4c at the end?
You would just do plus c at the end.
Okay.
So let's go back to the top one. So we have, what is the integral of 14x squared?
14x
Very good. What about 32x?
32x.
18x.
What about 5? 5x. And then, of course, we have this plus c here. 3, 4.
So the value of 5x.
What?
5x.
What is the derivative of 5x? 5. So the integral of 5 is 5x. The integral of a constant is x.
And then you can simplify those.
Constant times x. Yeah, you could simplify 4 over 6 and 32 over 2. Yeah, you could do that.
What I mean is that it's okay to do that. It's not like it doesn't change.
No, it doesn't change. So what I'm trying to get here is this is really, really powerful for any x to a power, right? So if I give you any constant times x to a power that's anything other than minus 1, you should be able to apply this theorem. So you take the power, you add 1, and divide by that new power, and then deal with the constant that's out front. So I know at first it was a little like, what are you doing? But does anyone have any questions now?
You said except for minus 1, are you just saying
Yeah.
minus 1 specifically? Or
Yeah, when the power is minus 1, we have an issue. So let's look at that. So kind of when I want to, so if I want to integrate x to the minus 1 dx, that might also look like the integral of 1 over x dx. I can't integrate that using the power rule because it would be x to the 0 over 0. X to the 0 is 1, that's fine, but I can't divide through by 0. So I can't use that rule. So this is saying I need to find the derivative of a function that gives me 1 over x. It is exactly ln of x. So if I integrate 1 over x, I actually get ln of absolute value of x because you can't take ln of a negative number. So you have to make sure you're taking the absolute value of that. plus c. So this is when your power of r is minus 1. Right? A lot of times on final exams I've seen the type of integral of like 3x to the 5th plus 2x squared plus 1 over, say, x cubed dx. So I've seen this one come up on final exam. So I need to break this up to specifically powers of x, right? So what would be the first one? 3x to the 5th divided by x cubed. That would be 3x squared. Plus 2, what's x squared divided by x cubed? X to the minus 1 plus x to the minus 3 dx. Do you guys see that? I'm just taking 3x to the 5th over x cubed plus 2x squared over x cubed plus 1 over x cubed. Yeah, I'm simplifying it. I'm putting it over the common denominator being x cubed, so then you get full, each one as a power of x question.
So what about if you simplify the x cubed, like we just use x to the power of minus 3?
Yes. 1 divided by x cubed would be x to the minus 3. Right? 2x squared over x cubed can be written as x to the minus 1. I see this one all the time on final exams, and almost always there's one of them that the power is minus 1, because you need to know that's ln of x, not minus or x to the 0 over 0 type thing, right? Because you're adding 1. So what is the integral of 3x squared? Yeah, so 3x cubed over 3. What's the integral of 2x to the minus 1? Very good. What's the integral of x to the minus 3? It's a little different, right? Because it's negative 3 plus 1. Negative 3 plus 1 is minus 2, and I divide through that by that same power. So we end up with x cubed plus 2 ln absolute value of x minus 1/2 x to the minus 2 plus c. So at this point, any power of x you should be comfortable with, right? So that tells you you can now integrate any polynomial, right? You should be comfortable with doing that. But we also know the integral of some trig and inverse trigs, right? So let's look at writing the differential point of view, the derivative formula. What's the derivative of sine? It's cosine. So that tells me now if I integrate both sides, that tells me that the integral of cosine with respect to x is sine plus c. What's the derivative of cosine? Is minus sine. So that tells me the integral of sine with respect to x would be minus cosine of x plus c. If I integrate sine and I integrate the derivative of cosine, I get cosine. So the integral of sine, the integral of minus sine is cosine. So the integral of sine is minus cosine. So this is easy to confuse, right? You know the derivative of sine is cosine, the derivative of cosine is sine, and there's a negative in there somewhere, right? One of them's negative, one's not. One of the derivatives is negative. You know, this is how you think, right? You know that much, and then which one's the actual negative. So if you remember the derivatives, which 4 chapters in you should be somewhat comfortable with derivatives. If you remember the derivatives, you can get the integration for free by just looking at this. If I integrate sine, I get cosine. Or sorry, if I integrate cosine, I get sine. So if I integrate cosine, I get sine. If I integrate minus sine, I get cosine. So the integral of sine is minus cosine. And the derivative is here. The derivative of sine is cosine. The derivative of cosine is minus sine. But if I integrate cosine, I get a positive sine. If I integrate minus sine, I get cosine. So if I integrate just sine, I get minus cosine. Because I can multiply through by -1, right? So then I have a minus cosine here and a positive sine here. The integral and derivatives cancel, just like what I did. If I take the integral of a derivative, I get the function. Right? If I integrate a derivative, I get the original function. Because they're inverses of each other. This is like saying you take a function and you subtract 2, then you add 2, you get the function. Which makes sense, right? So this is saying the same thing. So if I integrate this side and I integrate this side, it's saying the integral of cosine is the integral of the derivative, which cancels and I get sine. The integral of minus sine would be positive cosine. So the integral of sine is minus cosine.
I'm assuming it's the same way as with derivatives.
As we go.
Where you can take the second integral or third integral.
So you don't get into double integration until Calc 3.
Woo!
Yeah, in Calc 3 you'll see, and that's multiple variable calculus. Right now we're only looking at area under the curve of a flat surface. But double integration you can actually find volume. If I integrate something over the x-axis, then I integrate it over the y-axis, I would have a volume. And that's Calc 3. So, question?
Just as far as like the syntax is concerned.
Yes.
What we're saying, like on the bottom 2 lines, is, well, I guess more directly, when you're saying an integral of something, it's bookended by the integral sign and then dx.
Correct. Yes. Thank you for that. So I know I kind of threw out this notation without actually explaining what's going on here. So this integral is always with respect to something, just like the derivative is with respect to something.
Okay.
I differentiate this function with respect to x. Calc 1 is single variable calculus, so you only really ever talk about one variable. It could be t, it could be p, it could be g, whatever we're dealing with here. This also is with respect to a certain variable. And we're going to learn U-Substitution, which is actually we're going to say, oh, well, we don't know how to quite integrate this, but we're going to manipulate it to be an integral we know, and we're going to call this dummy variable u. Kind of what I did here. I said, okay, well, let's call r n minus 1.
Sure.
So n would be r plus 1. I could replace that to get it in a form I like. We'll be doing that tomorrow with this dummy variable. So it's important to kind of think of here that this du is what I'm integrating this function with respect to.
Got it.
In Calc 3, you might have a dx dy. So you're integrating the first function with respect to x, and then what you get out of that, you're integrating that with respect to y.
Okay.
So down the line, it plays quite a bit more important role. But yeah, anytime you have the integral sign, you have to have a dx sign. You will be counted off, just like you're counted off for limits if you don't have that. Okay, so let's kind of finish through. What is the derivative of tangent? Secant squared of x. So the integral of secant squared is tangent plus c. Widely always gives you the plus c, so sometimes you forget when you're actually writing it. A lot of times on the fourth exam, students put their name on it and then they'll put plus c and circle it. So then they go through and know to put plus c on everything that needs a plus c, because it will cost you some points if you don't. So the derivative with respect to x of cosecant. What's the derivative of cosecant?
No, negative cotangent close.
Very good. Negative cosecant cotangent. So the integral of cosecant of x cotangent of x would be minus cosecant of x plus c. What's the derivative of secant? Secant of x, tangent of x, right? So this is saying that the integral of secant x, tangent of x, with respect to x, is secant plus c. And then the last one, the derivative with respect to x of cotangent of x,
Negatives of cosecant squared.
so we have these 6 different trig functions. At this level, you will not be given a trig function that doesn't fit one of these. Calc 2, Chapter 7, there's a whole couple of sections about integrating more complicated trig functions. And you'll learn the integral of secant, the integral of tangent, the integral of cosecant, and the integral of cotangent. So I cannot, in Calc 1, we do not learn how to integrate just tangent, just secant, just cosecant, or just cotangent. That's Calc 2 material. So here, you'll be given one of these forms. It might not look like this, but it will be in one of these forms. So let's look at an example where it doesn't quite look like something you know, but it is something you know. So what is the integral of cosine of x over sine squared? So what's another way to write cosine over sine squared?
Oh, wait, that's sine squared.
So I could write this as cosine over sine times 1 over sine. All right? So that's going to be cotangent secant. Cosecant. Cosecant. Cotangent cosecant. What's the integral of cotangent cosecant? So this is minus cosecant of x plus c. But do you see here from here, you're like, ooh, what is that? But knowing that it has to be in one of these forms, getting it into that form and then knowing what that is.
Could you also do like a antiderivative chain rule type of thing with that?
No, definitely not. There is something we will learn U-Substitution, and there is another way to show this by doing a U-Substitution. And a U-Substitution is this dummy variable that we're going to say, well, we don't really know how to deal with this, but we would know how to deal with it in a different form, and a lot of times we can deal with u to a power. We know the integral of a variable to a power is really easy to do, and then we'll back substitute what that variable was. So here we might say let u be sine, right? And the derivative of sine is cosine, so nicely this cosine is going to cancel. And it's going to end up with u to the negative 2. I can integrate u to the negative 2, which would be minus, what would it be? U to the minus 2 would be u to the minus 1 over minus 1, right? And if u is sine, then 1 over sine is cosecant. So we end up with this exact same answer. And we'll learn that in I think it's 9.3, which will be tomorrow in this U-Substitution. So there is possible with sine and cosine, you can always do a U-Substitution because the derivative of sine is cosine, the derivative of cosine is minus sine. So there's always one you can pick to kind of cancel it out and simplify through. And get the same answer that we'll get here.
But like apparently the answer is not like equal to the original like integration. Like when we derive negative cosecant will be like negative cotangent.
If you integrate minus cosecant, you have positive cosecant cotangent. If you integrate minus cosecant, you can't integrate cosecant by itself in Calc 1.
Yeah, but I can integrate negative cosecant x, right?
No.
No?
You can integrate minus cosecant squared of x, because here, if I integrate minus cosecant squared of x, I get cotangent. This is already integral, so if you integrate this again, you're really doing a
I
double
mean,
integral
I
here.
find the derivative of this one to
This is an antiderivative. So if I differentiate this, what is the derivative of minus cosecant of x?
Secant minus cotangent.
It would be positive cotangent cosecant, which is exactly this. So if you integrate a function, you get a new function. If you differentiate that, you get the original function. In Calc 1, you cannot integrate cosecant. It's a Calc 2 problem. Cosecant, cotangent, tangent, and secant are all integration problems you do in Calc 2. So at this point, you can integrate these types of problems, and then tomorrow we'll learn how to integrate powers of sine and cosine questions.
So you couldn't do, like, since cosecant's 1 over sine, you couldn't just say let u equals sine and then integrate it like that?
Eventually, we'll talk about a U-substitution where you can let u equal sine. The only reason you can do that is because you have a cosine to cancel this dx. So if, like, I say, let u equal, this is what we're leading up to. You're going to be able to let u equal sine of x. So then du is cosine of x dx. Right? We have this integral cosine of x over sine squared dx. So if I want to manipulate this to be in something that I know, I'm going to use this dummy variable u. So hopefully I want to sine, so I can plug in u squared here. But the only reason I can do that is because if I have a cosine x dx, which is exactly what I have here, I can replace that with du. Because I can only have one variable in my integral. So this would be the same as integrating 1 over u squared du. And what is the integral of u to the minus 2? U to the minus 1 over minus 1, right? So this would be u to the minus 1 over minus 1 plus c. But this is in terms of u. If I plug it back in what it is in terms of x, I have sine to the minus 1, so that's sine to the minus 1 over minus 1, which or sine to the minus 1 would be cosecant, and then I'd have the negative, so I get the exact same thing. It's eventually where we're going. But at this point, in 5.2, if I pull up, let's see, cancel, this always does that to me, guys. So the last ones I need to talk about are the trig inverse functions. So while this is signing in, let's go ahead and mention the trig inverse functions that might come up. So do you remember the derivative of tangent inverse?
So yeah, it's 1 over 1 plus u squared.
Well, if I have a u here, it would be u squared, then du dx. But this is just in terms of x, right? So this is saying that if I integrate a function 1 over 1 plus x squared with respect to x, this is tangent inverse plus c. If I take the derivative of sine inverse, does anyone remember what this is?
1 over the square root of 1 minus u squared.
Very good. So in that case, if you're integrating something like this, that's tangent inverse. Or sorry, sine inverse. So there are multiple, or there are cosine inverse, which would be this one, but negative. And then secant inverse and cosecant inverse, tangent inverse and cotangent inverse are similar to each other. These are the two that I would expect you to know on a quiz or an exam. On the homework, it's possible the other ones might come up, but you can look those up from your book. Okay, so if we go back to some of the questions in this section, I've assigned 5.2, which we do a week from today. Most of them are kind of funny at the beginning. So it gives you that the derivative of this function is this. So if I integrate this function, I should get back the original function I got, right? So this is just setting you up to that if I know the derivative form of it, can I write the integral form of it? And they also give you this plus c, so don't write plus c in there, it won't accept it. Right? So the first one is just kind of to show you, eventually we'll integrate like this and get back the original function, and I'll show you how to do that as we go. But at this point, we're really using the properties here in this formula. So could you integrate 7x plus 5 over 7x to the fourth? What is the integral of 7x?
Or over 2.
Over 2, right? So if I put in, nope, that's not what I want. Over 2, I lost my 7, plus, so this is going to get, not too bad, so plus, I have a 5 over 7 to begin with. What is the integral of x to the minus 4? So the x would be in the denominator. What else am I missing?
Divide that by 3.
Divide it by 3, right? So it's going to be 21. Is it divided by 3 or minus 3? Minus 3. So there are multiple ways you can write this one. Any of them should be correct. Wiley should accept, as long as it is a fraction and not a fraction divided by a fraction. So the 5 over 7, and then this would be really x to the minus 3 divided by minus 3. So 7 times 3 is 21, and I pulled that negative out front. And then plus the 3 here. So if you put, plus, and then the minus down here, it should accept it. And it should also accept if you have x to the minus 3. Unless it says use positive exponents or something. So
when you're doing divided by minus 3, you're dividing by denominator by minus 3.
yes. So if I divide the denominator by a fraction, I really flip that and multiply it. And so sometimes writing that on paper is really beneficial. If I'm taking like x to the 3 over 2 over 3 over 2, that's the same as 2x to the 3 over 2 over 3. But if I just have x to minus 3 over minus 3, it would look like that. So Wiley should accept multiple versions of this with negatives questions.
What section is our quiz over on Thursday?
Your quiz on Thursday will be over 4.8 and 5.2. So pretty basic things from 4 to 5.2. All right, I will see you guys tomorrow.